Okay, next we're going to go over this question, which is a past paper one. So like before, we're given a language and we're asked to prove whether or not it's recognizable, decidable, both, or neither of those. So before we go on to what we should do, let's first understand what the language actually is. So it's all strings in this form. So hashtag X. So W and X are separated by a hashtag. Now what are W and X? Well, if you read this, you can see that they're an element of whatever this is. Now this over here is just a set containing 0, 1, and then clean start. What clean start basically means is you take the set and all its elements, and what you get is the set of all strings you can make with these characters. So you could have this, just any string you can make with the characters 1 and 0. So it'll be an infinite set of all these characters. And so if W and X are elements of this set, it just means W and X are some string made up of zeros and ones. 0 or more zeros and ones. So it could also be epsilon, or like the empty string. Okay, and it says that W has to be a substring of X. So what we have is two strings made up of zeros and ones, where one is a substring of the other. So W is a substring of. Now, just to go over what a substring is, if you don't remember from algorithms, a substring is like a string that is contained within another string. So a string is a substring of another string if that string is contained within the other one. So for instance, let's say these are two separate strings. Is this string contained within the other one? Well, it is, because if you look over here, this sub portion of the second string is exactly the first one. And so this is a substring of this. Now, can we create a Turing machine that recognizes whether or not one string is a substring of another? Well, let's think about it. As we said before, anything a computer can do, or a human can do, a Turing machine can also do. So if a human can figure out if one string is a substring of another, then so can a Turing machine. And if you can program a computer to do that, then you can also make a Turing machine do that. And if you remember from the algorithms module, they actually taught us a bunch of algorithms that you can use to detect if a string is a substring of another. And so you can basically use one of those and adapt it to Turing machines to answer the questions. So the simplest one they taught us is the brute force one. So the way this works is if we have a string we're trying to match, so this is the string we want to find in another string. This is the substring. This is the other string, the main string. What the brute force algorithm tells us to do is to go to every position in the main string, and starting from there, try to match it to the other string. So let's start at the very first position and try to match it. Do the first characters match? They don't. So we move on to the next position and try to do the same thing. Do the characters match? They don't. Move on to the next position. Do the characters match? They do. Okay, let's try the next character. Do they match? They actually do. On to the next. And now we've matched all the characters. Therefore, this string is actually a substring of this. So that's the general algorithm. We just need to adapt that to Turing machines. Okay, so because we know there exists an algorithm to do this, so like an algorithm that gives you a yes or no answer on whether or not a string is a substring. Sorry, I forgot to mention, if it is the case that, for example, we went through the entire string, we tried every start position, and we couldn't match it, And at that point, we know that this string is not a substring of the other one. So this algorithm gives you a definite yes or no answer on whether or not one string is a substring of another in a finite amount of time. Which means that if a Turing machine were to implement this algorithm, it would decide this language, and so this language is decidable because there exists a Turing machine. So let's write that out. So we're saying that L is Turing decidable. And we're proving this by construction. Okay, now we need to write out the steps the Turing machine should take to decide this language. The first thing we should do is check if the string is properly formatted. So for that to be the case, there has to be exactly one hashtag in the string. So if we look at this, W and X can be epsilon because of the clean star, and so the only restriction on the format of the string is the fact that there is exactly one hashtag, not zero and not more than one. So let's write a step to check for that. So we're going to, let me write this down first. So we're going to construct a Turing machine such that it follows the steps that we outlined. So first step is to scan through the string. And what we're going to do is scan through it and look for a single hashtag. So we're scanning through the tape from start to finish. Well, there's no finish, we're going to scan until we see the first blank character, which indicates that we've gone up until the end of the input. You can probably speed this part up because it's just a lot of writing. So if while we scanned it, we saw no hashtag, then we know we should reject. And if we saw two or more hashtags, so more than one, then we also reject. So if there was no hashtag, or more than one, then we halt and reject. Also, you don't need to write reject in all caps, but it just makes it easier to see where you've sort of ended the thing. Okay, so reject in this case, and if there is one hashtag, so otherwise, we move on to the next step. Okay, now this brings us on to the next point. Now we need to implement the algorithm. So we're going to try and match the characters in W with every starting position in X, which is the second string. Now this is a bit awkward because all this is in one string, and writing out this proof would be a bit long because you have to keep saying, go to the string before the hashtag, go to the string after the hashtag, because like these aren't explicitly named W and X. It's just some sequence of strings on the tape. Like this isn't called X, it's just 0, 1, 0. And so it would be nice if we could sort of separate the two into separate sections. So have W on one thing and X on another. And we can do that using a second tape. So we haven't gone over all the content, but all you need to know is that Turing machines can also have multiple tapes. And it's not really something physical, it's just an extension, it's like a convenience thing. You can sort of simulate having multiple tapes using the main tape. But for our purposes, we pretend like it's actual, like physically separate tapes. So what I want to do is to have two extra tapes. So let's say these are the, oh, one sec. Let's say we have two extra tapes. Each of these tapes have a separate read head, and the Turing machine can access all of them at the same time. Let's say our input was this. What I'm thinking of doing is putting W and X on separate tapes. So this is W, the part up until the hashtag, and this is X. So we could put these onto separate tapes, and that will make it a bit easier to write out the proof. So we could write a step to move this onto the first extra tape, and move this over here. And we could do that easily. We just keep moving the read head, and we keep copying over the characters one by one onto the other tape. So for instance, to copy W, we read in a 0, copy it here, shift the read head, copy 1, shift read head, copy 0, and then we reach the hashtag so we know W has ended. Then we do the same procedure but for the other tape, copying it over. So that's how you'd copy it over. Okay, let's say that in the proof. So let's say we will use extra tapes. So first let's do the second tape. So use a second tape. And this means that we're using a multi-tape Turing machine. So let's just mention it. You're allowed to do this in the exam. It's in the slides if you want to go over why exactly you can do the multiple tape thing. Okay, so we're going to copy over. So we need to copy over W, which is up until the first hashtag. So we're going to say that. Let's first say to put the read head at the start of the input just in case it isn't already there. And we'll call the original tape the main tape. So we're going to copy over all characters up until the hashtag. Onto the second tape. Such that the tape now consists of W. From the original string we had, which is this. Okay, and let's just give this tape a name so we can refer to it easier in the future. Instead of just saying second tape, let's just call it the substring tape. So, just to reiterate, this tape will now contain all the characters to the left of the hashtag, which is effectively W. Okay, now we're going to write out the same thing, but for the third tape. So use a third tape. Now let's say to put the read head of the main tape at the start again. So when I say this, I just mean, oh sorry, not the start. Okay. Put a read head of the main tape directly after the hashtag. So we're just saying for the main tape, you want the read head to be right here. And then we keep copying over string and characters as before, but onto the third tape now. And what do we copy until? We copy until we see a blank. And if we do this, then this tape should contain X. So it consists of X from the original string, which was in the form of this. So let this be, let's just give it a name, we'll call it let's call it the main string tape. Because we have sort of one main string that we're trying to match the other string onto. So we're calling W the substring and X the main string. Okay, now that we've done that, we have the strings on separate tapes. We can move on to the main algorithm part. Okay, so let's go over what the brute force algorithm would look like on the Turing machine. Before that, let's just do a quick recap of what it is in general. So let's say this is the substring that we're trying to find within another string, and this is the main string that we're looking inside of to find the substring. Okay, so what we would do is we'd go through every starting position in the main string from left to right, and we try to match all the characters starting from here with the ones in the substring that we're looking for. So, are these characters the same? They're not. And so what we do is we go to the next starting position to see if we could find a match. Are the characters the same? They're not. So we go to the next position. Now, are these characters the same? They are. So that means we've just found one match. And so now we need to match the next character with the next character in the main string. So are these the same? They are the same. And so we've matched the second character. Now we have to try and match the third character. Are these the same? They're not. And so what we need to do is sort of reset the substring matching because we failed to match the third character and now we have to try again. But what we would do is go to the starting position that was directly after the previous one. So before the starting position was here. And so we wouldn't start trying to match from here immediately. We would actually go to the next one after the previous starting position. So originally we were over here, then we tried to match, we got up until here, but then we failed. So if we were to just start matching from here immediately, we would have skipped this position being the start one, so this one. And so because we don't want to do that, we need to return to the previous starting position and go one to the right. And so we need a way of remembering what the previous starting position is. And so what we would do is like, for example, mark it. So say we were doing the matching, we skip this, start here. These were matching, and so we go to the next one. But we want to remember that previously this was a starting position. And so we sort of mark it like this. And then, as before, we would have matched this, try the next one, but then it failed, and so we go back. And then we just go to the next one and try this new starting position. So, are these the same? They're not, so we just go one to the next. Are these the same? They're not, so we go one to the next. Are these the same? They are, so we try to match the next character. Are these the same? They are, so we match the next character. and these are also the same. And now we've managed to match the entire substring, and so we know that it occurs within this string. And so the answer for this would be yes, there is a substring. But for example, let's say the main string was like this, and we were back over here. What would happen? So we would try to match these. They match, so we increment the thing. And again, we remember that this was a starting position just in case we fail in the future. And so we match this, they're the same. So we increment both thingies. We try to match them, but they're not the same. And so we return to the previous starting position and reset the thing on the substring. Return to the previous starting position, go to the next one, try to match them, not the same. Go to the next one, try to match them, they're not the same. Go to the next one, try to match them, they're the same. So we remember the old starting position, and we increment both thingies. But then we've reached the end of the main string, and so there's no more characters left. And that means that there wasn't a single substring occurrence of the string in the main string. And that means we failed to find a substring. So in this case, we would want to reject. So essentially, if we manage to go through the entire main string, all the starting positions without finding a complete match, then we reject. But then if we manage to find a match, we accept. And so no matter what, we have like a yes or no answer. So let's translate that to Turing machines. Let's say this is the substring we're trying to find within another string. So it's very similar to before. And this is the main string. So again, what we need to do is try to match each character. So they're not the same. So therefore we move the main string read head to the right. They're the same. And so we need to remember that this is the previous starting position, and then we increment the read heads. Now the way we would remember this in a Turing machine is we need some way to mark the character. So we could do anything. We could just replace it with like an X, or we could replace it with like 0 with a dot on the top to represent it being marked. So let's do that. Replace it with that to represent that we're remembering the starting position. Then we increment both read heads. We look for a match. They are the same. So we increment again. They're not the same. And so we reset this one. Then go back to the previous starting position. And we know the previous starting position will be the first marked character. So we go here. And then we increment the main string and try the next starting position. Now, these two characters the same? They're not, so we increment. Not the same again, increment. They're the same, so we mark the character and increment both to try and match the next character. They're the same, so again we do this. And they're again the same, so we do this. Now we've reached the end of the substring input, so we match the entire substring, therefore we accept in this case. Now we can recognize that if the substring read head reaches a blank character, so that means we accept. And so that's how it would work on a Turing machine. But we just need to write that down like a sequence of steps that the Turing machine can take. Okay, next let's go over Okay, next, let's go over the steps the Turing machine should take to implement the brute force algorithm. So first thing to remember is that we already reset the read heads of both tapes to the start, and so we don't need to do that again. So we can move on straight to the main part. So first, remember we're going through every single starting position on the main string tape up until the blank character, so the end of the input. So let's write that down. So for each starting position on the main string tape, which I'll abbreviate to MST, from the left to the right up until the first blank. Oops. So what we want to do is compare the characters under the read heads of both the main string tape and the substring one. So MST and substring tape read heads. Okay, so first thing to check is that the character on the substring tape is a blank. If the substring tape's character is a blank, then remember that means we match the entire string, and so we want to accept. So if the character under the substring tape read head is a blank, we halt and accept because we matched the entire substring. So we'll just say W has been found in X. Okay, so we checked that the substring tape read head is a blank. Let's go over what happens if we find out that the character under the main string tape is a blank. So remember, if the main string tape reaches a blank character, that means we went through the entire string and did not find a match. Because had we found a match, we would have halted and accepted. So if we manage to reach a blank character on the main string, then there's no match, and so we want to halt and reject. Oh my days. Okay. Okay, so I hope this is readable. I wrote it down as no substring match was found. Okay. So we've covered the two sort of base cases. Let's move on to the main thing. So if the two characters under the substring tape, under the tape read heads match, so if the characters, so the characters here are the ones that we're comparing. Okay, so if they match, and if this is the first character we're matching on the substring tape, remember that we want to remember the starting position we're using on the main one. So if this is the first character of the substring tape being matched, then we're going to mark the character under the main string tape read head to remember the starting position that we're using. And we're just going to clarify that by marking, we mean that we're going to change the characters to like an alternate form. So 0 turns into a 0 with a dot if we're marking, and the 1 turns into a 1 with a dot. But you could do anything. You could like cross it out, you can just say whatever, it doesn't really matter. And if the characters did match, we also want to move the read heads to the right by 1. So we're going to try and match the next character. And just to clarify, sort of this thing that we're doing is separate from the if statement. So we're doing this regardless of this, if this was the first character. So to make that a bit clear, I should probably move this to its own. like this, just so it's a bit more clear. Okay, otherwise, if the characters don't match, then we're going to reset the substring tapes read head to the very left, because we need to restart. And then we want to move to the main string tape read head to the next starting position that we want to try. So to do that, we first move it to the marked character that we marked before. So move the main string tape read head to the left until the first marked character we see. And then we move it to the right by one, so we're trying the next one. And if we do this, we want to go back to step 3.b. So we just start the comparison process all over again. Okay, and that's basically it. This is the entire sort of algorithm that we wrote down. It's quite a lot of writing. You could probably make it more concise, but if I were to do an exam, it would be something similar to this. Okay, so now that we've written out the steps and the algorithm, we need to write out our concluding statement where we conclude which of these the language was. So one thing I forgot to mention is that because the language is Turing decidable, it is actually both decidable and recognizable, because decidability implies recognizability. So it's both, not just decidable, which was a mistake I wrote before, accidentally. Okay, so let's write out the concluding statements. So here, we need to mention that the algorithm for the Turing machine that decides the language is completed in a finite amount of steps and takes a finite amount of time, and therefore the machine will never loop and will always halt. So we need to explain why that is the case. So what we'll do is we'll say that because the input is finite, this step where we go through every start position will be completed in a finite amount of time because there's only a finite amount of possible start positions. It's not infinite. And so all this comparison stuff will also take a finite amount of time. And therefore the entire thing takes a finite amount of time. So let's say that. So because the step slash algorithm described takes a finite amount of steps, amount. And let's just mention that there are only a finite amount of starting positions. Let's also say the input is finite in length. So step 3.a will take a finite amount of steps. Slash time, as there is only a finite amount of possible start positions to go through. To iterate through. And for a similar reason, the comparison step also take a finite amount of time. So therefore, the Turing machine never halts. Ah, sorry, never loops infinitely. So it'll never loop infinitely, and will always halt in infinite time, and it will always output the correct response. So like an acceptance or rejection based on if the substring was in there. So because of this, so by construction, which is our proof method, as you can see over here, proceed by construction. So by construction, we have created a Turing machine that decides L. So that means that L is decidable, and because it is decidable, it is also recognizable, which means that L is both decidable and recognizable, which is the final answer. Okay, here's what I wrote here if you need to read it. Here's the main algorithm part. The key thing is that it's both decidable and recognizable. Okay, that's it. And if there's any part of it that wasn't clear or you need some help, just let me know.